Hi, Chris Leon here for LMC 6310, Computing as an Expressive Medium, graduate level course, Georgia Tech Digital Media's program. This is going to be a little bit longer than the other videos in this series. This is part of a number of videos in this series, so if you're coming in new to this, you're a little bit lost, recommend you check this channel to find the older videos in the sequence for Introduction to Programming using Processing. So although this example is based in processing, what I'm showing here is going to be collision detection using a two-dimensional grid, which is an optimization that's been around since it's been popularized by games like Pac-Man and Super Mario Brothers, but it was really around long before then, and has been used in a number of games, a number of platforms outside of that space as well. It's just a very general way of handling collision detection in a way that, even though we're doing it in processing, you could implement in C or C++, ActionScript 3, all kinds of other platforms as well. And to begin with, we should open up processing. Notice I'm on 2.02. Newer versions, older versions may have slight differences. In most cases, you're probably going to be fine. But if you want to be certain that the code I'm writing here is going to work for you, you can download 2.02 from their website at processing.org if that's not the one you're on. As always, we're going to begin with a void setup and a void draw. If you ever find my text is too small, these are recorded in HD 720, so you should be able to use the gear icon in YouTube to get higher resolution view and full screen it. We're of course going to set the size of our window, which I think we forgot in previous videos, 600, 400 gives us a good sized window. And I know I've said this before, I know you're probably coming to these videos after having seen the previous ones for a while now, but I do want to emphasize that that's not 600,400, that's 600 pixels wide, 400 pixels tall. The comma is used to separate the argument, not to separate chunks in a number. Now let's begin with having a shape that we can move around, which, as always, I like to begin kind of hacky, and then move towards classes and organization beyond that. So we're going to have a player X and a player Y, and let's draw an ellipse where that character is. Let's draw a rectangle. We're also going to have a background call, just going to black out the screen each time. Then we're going to draw at player X, player Y, a box which is 10 pixels wide, 10 pixels tall. So of course, as always, the rectangle by default is indicating our top left corner of the box, and then a width and a height. And then we're going to have some key input that'll help us move it. So, let's see here. We're going to have void key pressed, I believe. And here we can check and see if key code equals right. We're going to do player X plus plus. We're going to save our sketch just so we have a name to it. I'm going to call this sketch grid collide. Now I realize I might have covered some keyboard input in the previous video a little bit. It's going to build off that a little bit too. So there's a character. You can see this white box right here when I press play to run it. And when I hold down the right arrow key, it moves us right. But of course we want to have a better system for doing this. We want to be able to hold the key down. And in case it's not apparent, we can make this character start further into the middle of the screen. This will change its start coordinates to 100 pixels wide, 100 pixels tall, 100 pixels, sorry, from the left side of the screen and from the top of the screen, since that's the coordinates we draw at. And you'll notice that, so there it is, 100 pixels in, 100 pixels down. Remember too that the X and Y have no special meaning to the programming language. They're just our designators to help us keep track of which one we expect to use for each position. But it's really up to what order we put these in. We could put player Y then player X and player X, and we would just get results that don't make sense to us in terms of mapping to what we expect for the X and Y coordinates. So I'm holding down the right arrow on my keyboard, which is why it's shuffling right as I hold down the right key. But of course what we want to do is Boolean Hold right. We're going to keep track of a variable for when the key is held down. So when you press the right key, it's going to turn this number, it's going to toggle this to true. When we press the release, and I apologize, this is kind of a review for you, but it's going to be foundational to us navigating that grid. So if when the key is released, it's right, then we'll set that to false. Remember that key pressed and key released, just like void setup and void draw, are built into processing, and so those get called automatically each time the key goes down or when the key goes up. And no matter what key does, this function block with the braces for key pressed gets called. No matter what key gets released, spacebar, J key, 4 key, this key block will get called, which is why you have to use this if key code filter to catch if it's a key to the right. Now remember too that if we want to check a key on the keyboard, like I say the letter J or something, then instead of checking key code, we would check key instead and use single quotes around it to demarcate which key we were looking to detect. But right now we just want to use the arrow keys. And now all we're doing so far is we have a new Boolean variable. Boolean meaning it can be true or false instead of a number, instead of a decimal point, instead of a word, just a true or false. Defaults to false, turns true when we press the right key, turns false when we let go of the right key, but we haven't yet handled that input. And so we might add a block of line here in our code inside draw being what's called every single frame. If the right key is being held, let's add to the player's X position, plus being 2, again, the same as plus equals 1, or the same as player X equals, so the same as plus equals 1, or the same as player equals player X plus 1. Since we want to take the value that was inside the number, add 1 to it, and put it back into the original value. Plus just being the shorthand for doing that. So I should now be able to hold down the right arrow, and it moves smoothly instead of in sort of jumpy increments. And when I let go, it stops. That works. Once again, before we even wrap something into a class, we can start doing it as a new file, which in processing is a new tab. I click on this arrow up here. So I right-clicked, new tab. I'm going to name my new file. I'm going to call this one keyboard because it's going to be a file for keyboard stuff. I'm going to go ahead and move hold right over there. I'm going to go and move key pressed and key released over there as well. And this little block here, you'll see we might want to move that over there too. So let's make a new function, void handle key input. Handle key states might be a better way of calling that. State being just know whether it's held down or not. I'm going to move this code from void draw, this if condition, check if the right arrow is being held down, move the character, into handle key states. I'm going to call that function here inside void draw. Doesn't really matter where in the void draw we call it, but I'm going to call it the start. So remember that when we get to this function we defined, so unlike draw, which is called automatically, unlike press and release, which are built into processing to be picked up on certain events, we're only going to call this bit of code top to bottom when we hit this label, which we're putting inside draw ensures it'll be called every single frame. And there's one less organizational move, although this would work the same. I'm just going to take that new function we've written, void handle key states, again camel casing my name just for convention's sake. I'm going to move that over into keyboard as well, so that as much as possible our keyboard information is all tucked away in one file. And so we've got in here our Boolean, our key pressed and release conditions, our key states handling. Other files just setting up the resolution, checking the changing the position of the player based on the key states, and then updating the display in terms of redrawing the background. Remember, if we comment this out, we would just leave a smudge behind the character, but that's erasing each time the previous frames, and drawing a rectangle at the player's position. There we go. Let's change our character now so we can move it in 4 different directions, and I'm just going to do a little CopyPaste Magic. Copy, hold left, hold right, hold up, hold down. There's more elegant ways we could try to handle this if we wanted to scale better. I think this will work for now, at least. I really like the conceptual purity of what we're doing here in terms of being able to really follow what's going on with the code rather than having some sort of complicated state table. Up and down. As always with copying and pasting, you want to be careful that you don't mix any variables up. So right in all capitals indicating the right key arrow. Hold right. Left meaning left arrow, hold left. Up meaning up arrow, hold up. Down meaning hold the down arrow will be hold down true. Recall as always that capitalization counts in programming, so if you mix up this programming capitalization, you'll probably get an error. And again, to not feel bad about errors, that's just part of programming. I copy and pasted the block, all of the code from key pressed because I already matched all those up. I pasted that into the guts now of void key released, and I'm going to replace in each of those true with a false, so that when I press a key, it's going to turn those states to true. When I release a key, it's going to turn the corresponding state to false. So remember, this even allows me to I'll press the up key, so it'll go down. I'll keep holding it. Then I can press left. Left will turn true. I can release left. Left will turn false, but up will still be true until I release up, because of how we've written these key pressed and key released functions. We still need to handle those inputs in the same way we've. Oh, sorry about that. In the same way we've handled hold right here. 2, 3, 4. Copy and paste those. Left. Remember that left means that the x value is decreasing on our screen. Up and down. will affect, instead of x value or y value, notice I've changed these two player values to player y instead of player x, because we want to affect the vertical coordinate. And also, I always voice that every time, vertical space is flipped in a computer graphics situation, in most computer graphics situations, at least on a 2D plane, as compared to what you're used to from, say, geometry class, where negative y is actually towards the top of the screen because of how things are arranged in memory. And so if that all worked, you should now be able to use the 4 arrow keys to navigate the character around in 8 different directions, not only up and down, left and right, but to be able to hold the diagonals to achieve diagonal movement in any sort of cardinal compass, northeast, southwest, as well as northeast, southwest, southeast, northwest, and so on. So we can now have a character that moves around freely within that space, but we don't have any walls yet. And walls are really what we want to get at. Walls are the bulk of our interest in what we're trying to do today. And so to begin with, let's start off by drawing our walls, by laying some walls out. To do that, we're going to keep track of a grid. And a grid's going to be, as always, I'm going to start this off in the main space. Now notice too, actually before I do that, that keyboard is just a separate file. It's not a separate class. We don't even have a keyboard class. We haven't declared one. For the program like this sake, the scale, this kind of works. This all falls into the global category of code. The place where that can screw you up is if you lose a brace off something. If you have too many braces, it might indicate your error is in the wrong file because it's trying to figure out it. The brace is its only clue as to where that file began and ended when it started compiling. Okay, let's start building a world grid, which I'm going to begin by saying int, and this is 2 brackets, indicate a 2-dimensional array. You may remember array lists and arrays from earlier topics in terms of being just a sequence of numbers we can keep track of, each with individual indexes or addresses, so a series of integers. Having 2 of these makes a 2-dimensional grid for us, so we can keep track of, like a battleship grid, B7, except instead of B, it's numbers along each side, so it would be like 3, 7, 7, 2, would be different positions in the grid of numbers. You'll see what I'm talking about here in just a second. And we're going to say world grid, and let's define it in line. I'll show you what I mean by that. So first off, let's start pretty simple here, and I'll say 0, 1, 1, 1, 0, 0. Just going to try to make a pattern that's going to be easy to see when we display it. 0, 1, 0. And so the idea here is I'm going to be graphing out a space which is has an empty and then 2 bricks, a brick, and then 2 empties, an empty, a brick, and an empty. This might make more sense if we start to build this out a little larger. Now with that, we can display it. Is what first thing we're going to try to do. Before we worry about collision with it, let's just figure out a way to draw it and what that's going to involve. So let's make something called draw world grid. Actually, let's make that world draw grid. And you can see, as I often do, by starting off with a noun, I'm kind of setting myself up for, I'm going to probably migrate these to their own file, world. If I want to wrap this up in a class, then to better isolate that code, I can. But this sort of habit helps me keep segmented which code is for which purposes. Now to draw the world grid, we're going to have to iterate through each row in each column. So how do we do that? Well, you might want to first go through each, you might think of it as so left to right, top to bottom. Remember that the inner loop is going to be the one that deals with the left to right, because the outer loop is going to step us down row by row by row. So let's first say int row equals 0. Row is less than how many? 3 in this case, and we can get the number off of world grid. Let's for now just put 3, and we'll show in a second where we can define that to be more useful to us. And then row plus plus. So that means it's going to go start at the top row and go down through each row. Let's set up one for column. Go down through each one. And now here we've got to make a decision for how we want to draw, how we want to represent these world grid values on the screen. And so the first thing we want to do is we want to check and see if the world grid at the corresponding row and column is a 1 or a 0. Now maybe you're wondering how do we index that? It's kind of a little counterintuitive, right? Because column is going to be your second number, row being your first. Because if you look up here, row is like 1, or 0, 1. So now we're in the 0, we're in the first row number 1, row 0, row 1, row 2. So it was row, and then column is how many steps in. So 0, 1, 2. And so they say if it's 1, then we'll set fill color to, let's say, green. That'll be, there we go. 0 red, full green, 0 blue will be green. Otherwise, we're going to assume it's an empty tile, which for now we're going to make bright red. Full red, 0 green, 0 blue. Full red, 0 green, 0 blue. And this won't be very sightly at first, so we're just kind of getting started out. And now how to represent those spatially is going to come down to how big we want the grid spaces to be. We know we're going to draw a rectangle, just like a chess or checkerboard. Let's say we want it to be, well, there's 4 arguments here, right? There's the horizontal position, there's the vertical position. These aren't going to stay, it's just us thinking through what we're going to put there. There's the width and the height of each square. Let's say we want the squares 50 by 50. Seems reasonable, I think. And now if we want the squares 50 by 50, then where do we position them on the screen? Well, so if it's the very far left side, then we know we want it all the way against the edge. And then for each column over, it should be 50 more pixels. And so if the x position is based on the column, then column times 50, vertical position, row times 50. You'll see what we've done here is just taken the assumption that because every tile is 50 pixels, we can skip ahead. So if we're on the third column, 3 times 50 will put us over 150 pixels for our left side. And we still need to call this function from void draw in order to see it. Make sure you put the call for this function after background, because remember background is going to wipe the screen black, and we want to be able to see what we're drawing. So let's see if that worked. Hopefully it did. It seems to have. You can already see here, there's my shape. I'm going to move around. Okay, so first of all, our shape you'll see is now red because we changed the fill color here. The last brick that got drawn was red, and I didn't yet update the fill color for the player. So let's change the fill color for the player to white. So here I put a fill with 255, 255, 255. I could do 1 255. I'm going to stick to all 3 in case you want a different color. It's easier to change. There we go. So now we have there's our player position. And you'll see there, pretty plain as day, that's our world grid. See these layouts of zeros and ones? There's a 0, 1, 1, 1, 0, 0, 0, 1, 0. And all we're doing here is we're looping through, again, row by row, within each row, column by column. We're checking to see if the value at that row and column in the world grid, this 2-dimensional array we've arranged up here, is 1. And if it is, we're priming the color to be green, which is why you see greens correspond to the same pattern of ones up here as you see over here. Otherwise, we're setting it to red, and then we're mapping a rectangle to that multiples of the tile width over and in. Now, there's lots of numbers floating around here that are kind of unfortunate, right? Because the same number here needs to be the same number there. Same number here needs to be the same number there. Let's go ahead and define those in a more public place. Now, before I do that, I'm going to go and migrate in this world code. As I kind of gave a preview to earlier, I'm going to move that over to its own tab. So I'm going to say new tab. I'm going to call this one world or map or whatever you might like. I'm going to cut with Command X, Control X for you Windows users, world grid and world grid draw. I'm going to move those both over into world. So I've just moved those both over here. I just kind of keep myself a little tidier. I saved Command S or Control S for Windows folks. And again, we still need to have this function call here, which is going to allow it to make this code happen. But now we've got our world code in one place. And that's going to make it easier for us to define like final int, let's say grid tile width 50. Grid tile height equals the same as grid tile width. And now I can take this number, this 50 up here, and replace here that the number of columns in is really times grid width. There's grid width. Grid height. I'm going to replace the 50s down here with grid height. And that's just going to help me stay organized in terms of knowing what those numbers mean, so I don't just have these 50s floating around. And I could change them up here in one place. Say I want a bigger grid, twice the size. Now when I press play, there's my bigger grid. And you'll remember that our player character is starting at 100, 100 on the screen. So that's our proof that our tiles, notice we're right at the corner of the very first tile, is 100 pixels in, 100 pixels tall. We have now doubled the dimensions of our grid space. We can then use those same values when we're computing collisions against the walls. Although this, so far, isn't going to be a very good grid to collide against, right? I mean, these are pretty big units. We can't really fit a whole lot of map on the screen at once. Let's decrease the number back down to 50 for starters. Let's also say we want to increase the dimensions of our world grid. One of the few different ways we could do it. We could define a constant for it. Let's try. I'm actually not sure if it'll let us do this, so we're going to explore together. Row dot length. Will it let me do it? Totally will. Okay. World grid dot length. And sure enough, what should happen? Yes. So what I've done here is I've utilized the dot length value that we can use for arrays and processing to get the dimensions of that array. Now we could instead globally define a variable up here and then reference it down there as long as we kept this grid in sync with it. But what's nice about this is that we can now add a separate row or a separate column to our grid in the map. So see, I've just added an extra comma space. So we now have a 4x3 map. And when I press play, there's a new 4x3 map. And again, notice that the ones correspond to where it's green. If I want to add another few rows, I can just copy and paste this row a few times. Maybe I'll change the pattern around a bit. Put a block of red here in the middle. There's some spacing. Put a little hook here. And when I press play, you'll see now, once again, that corresponds to our figure of where the ones are in my grid. And your ones might be in different places. That's fine. We're going to write collision detection code in a second that's going to determine whether or not we're currently on top of a grid unit that has a wall there. And now we could take this further. Let's make our map twice the width. Okay, so I'm going to copy this entire block. I'm going to put a comma and paste it. Comma, paste it, comma, paste it. And I'm just trying to very quickly and easily double the width of my map. And I might make a few little minor changes just to help prove to myself that these are all separate rows, that it's still lining up with my grid. But again, your figures don't have to exactly match up to mine. That's not so important. But we can see here indeed that there's a block of 4 number ones here. There's my greens. There's some ones. There's some ones. We just want these two to match up because we're going to start writing collision code based on where there are or not ones. Now we've got some sort of basic structure in place. Let's go ahead and zero out our grid. I'm going to put zeros in most of my grid spaces. Except I'm going to start building little test areas to try bumping my character around in. So that as we write collision code, we'll have a little section to test. Okay, so first of all, I've zeroed out my entire grid. And sure enough, if I press play, it's all red so far. I can add maybe a little room of ones. And let's see, when I press play, that starts me out right here, which is kind of a nice little spot. I'm going to actually decrease my grid size a little bit. Instead of 40, instead of 50, let's try 40. See how that looks. Yeah, it's going to be handier. Notice that this starts us in the center of a tile, which is going to be easier while we're just sort of working on our initial collision code. So I got some little walls there. And maybe we'll have a little standalone brick out here to try bumping against. There, it'll be there. And I can put some walls up along the corner if I so please. But you start to kind of like just see the grid and start seeing these numbers. And one reason why we're using integer grid as opposed to say a binary or a Boolean grid is that these numbers actually will become key codes for us as we move forward. So we can have different numbers to indicate where we want the player to start or where we want power-ups to be, where we want enemies to spawn, as well as different types of walls, where there's doors, where there's keys, where there's treasure chests, where there's stairs. These numbers can become key codes into us to mark our map, having different sections that we can handle different ways in our code, either right when the level loads, as is the case for like a player or an enemy start position, or even throughout the gameplay experience, as is the case for where the walls are, where there's spikes, lava, and so on. Okay, so we've got a little grid now. Now we need to find a way to detect if the player is on a grid space. And the way we're going to do that is we're going to write a little function that's going to tell us back what we're standing on. Int what is under this coordinate. Int this x, int well, let's say, this means particular things in programming, so we're going to avoid that. Int sum x, int sum y. And now, the way to go backwards. So first of all, we want to figure out how to map the player's position. Remember that so far this is just an empty function. Safe to run, it's not even up. That was right, we have to return an int. We'll return 0 for now. So I'm going to press play. And one thing we have kind of wrapped up in our minds we haven't put anywhere is like, what does 0 mean? So here's another handy use for these final integers, where I can say final int grid type space equals 0, grid type wall equals 1. And so now I can return grid type space. I could go here and pound all these out to be space and wall defines. Instead, I can use this as my key so that when I look at my grid, I know what the numbers are to expect. I can return those types from what is under this coordinate. And when I check this value elsewhere in the code, I'll be able to check it against, is it a type wall, is it a type space, without having to know how those are defined inside our wall or our world file. But so we're not really using this function yet. I just want to look at this grid one more time to think through, okay, we have a player position on the screen. So remember, it starts at 100, 100, which is about here. And as it moves left, it gets less. So like here, the x coordinate 0. Here are the y coordinate 0 as well. We want to think about how to turn those into tiles. Well, if these tiles reach 40 pixels wide, right? So we can even do this. Let's come over here. We're going to draw to the screen where our mouse is, just for convenience sake. I believe the coordinates come after. Let me try. Text. Probably, yeah, I got it the other way around. Okay, text will come before the mouse x and mouse y. Again, I apologize. I've jumped between a lot of programming languages for a lot of different reasons. Okay, so we have text that shows up in the mouse. You see there I've got text on my mouse. We're going to make that be our mouse coordinates so we can see where our character is located. Plus mouse x, plus comma space with quotes around it, mouse y. See, so this is going to start off with, let's say, parenthesis, and a right parenthesis. So I'm just going to add a parenthesis. It's going to concatenate using the plus sign, the current mouse coordinates, how far it is from the side of the left side of the screen. I'm then going to concatenate in with quotes around it because it's a string, a comma and a space. So we'll have mouse x coordinate, comma, space, mouse y coordinate, or the height from the top of the screen, and then the closing parentheses. So this will let us see, there's where our mouse is. See that? Now instead, though, we can use that to visualize player x and player y. I'm going to keep it positioned at the mouse just so it makes it easier for me to display. But my goal here, see, so we started 100, 100, which is why you see that on the code. I guess probably that way for y'all. And you'll see how when I use left and right, it moves my character back to 0, moves my character up when I go to the right, and likewise notice how it affects the y values. So let's think through, okay, well, how do we find that coordinates position on the grid? Well, so as long as our x value is less than 40, then our corner is in the first tile. As soon as it's more than 40, we're in the second tile. If you watch it, when it's at 80, we transition to the third tile. 120 transition to the fourth tile. Just because, remember, so it's just like we multiply by these numbers to figure out the left edge of each tile we're drawing. We can divide by 40 to figure out which tile we correspond to in the grid. So here we're at only 20 down. Here we're at over 40, so we're into the second tile range, third tile range. And actually, let's go ahead and change. Right now, we've been drawing the player as a rectangle. We're going to change that to an ellipse. Remember, an ellipse is just like a circle with a separate width and height, so you can make it stretch like an oval. An ellipse, unlike the rectangle, draws at the center of the coordinate. So this will make our collision detection a little easier to think about while we first start doing it. So that right now, if I'm at 40, 40, thereabouts, you can see I'm roughly there on my mouse position over here. Then I'm basically on the intersection. Otherwise, when we use rect, we're thinking about the top left point. We have to start thinking about the width and the height of the figure as opposed to just being able to treat it like a point is easiest at first. Okay? So we have a way now to display the player's coordinate. Now we want to translate that coordinate into the tile positions and figure out what kind of tile position is underneath the player there. So let's say some tile row. So how do we find which row the player is in? Well, we can take the player's y coordinate and divide by the height of a tile, which in this case is 40. How do we find the column that the player is in? Take the x coordinate, divide by the width of the tile. And I realize it can be a little counterintuitive, right? That it's kind of like latitude and longitude can throw people off. Columns are vertical, but that means that you count columns to figure out how far you are horizontally. Likewise, rows are horizontal, but you count rows to figure out how high or low you are vertically. These things that can throw you off at first if you're new to it. You get used to them pretty quickly. Now, the other thing to think about is we need to bounds check these, because one of the deals about primitive arrays is that if we try to access a position that's not in the array, if we try to check a negative coordinate, if we try to check 80 tiles over, it might crash our program because it doesn't know what to tell us. It doesn't know what to expect. So the right way to handle that is instead to do some bounds checking on our own. We know those values should never be less than 0. And what we can do is, if we find that we're trying to get a position off of the grid, we're going to kind of cheat a little bit, and we're going to tell it that we found a wall there. What that's going to help us do is we'll write collision code to say, okay, if the player bumps into a wall, reverse the player's position. That's going to work because if we try to leave the map, it's going to act just like it ran into a wall, like there was an infinite wall in every direction off the map. So if the column that we find is left of the map is less than 0, then we're going to return, I think it's grid type wall. Let me double check up here. Yes, grid type wall. Okay, we can do the same check there for if our row is less than 0. Now what do we check to see about if it's greater than some value? What value do we want to compare it to? Let's think through that for a second. If we look at our loops that we did, for a row comparison we checked the length of the world grid, and for the column I checked the row's length. What you got to remember is that this is a two-dimensional array, and so each row has its own length in terms of columns, and this is just making sure that what we're getting is the actual length of that row. We could have uneven rows, probably. I wouldn't recommend it. It's kind of a wonky thing to do. We're going to keep those two pretty tightly coupled just for sake of clarity. But row, you can see here, we check against world grid length. But remember too that we don't actually want to see if it's just greater than, because if there are 5 entries in an array, arrays are 0 indexed, and so that means that there's a 0, 1, 2, 3, and 4. 0, 1, 2, 3, 4 are the index arrays into a 5-element array. And so if our grid length is actually 5, we don't want to see if it's greater than 5. We want to see if it's greater than or equal to 5, because 5 is also not a valid index into an array with 5 entries. 0, 1, 2, 3, 4, 5 doesn't exist as an index for a 5-entry array. So we want to check greater than or equal to. Unlike these, where 0 is a valid entry, but the length of it itself is not. Now, one reason why we wouldn't want to keep, or why we do want to keep our rows of even size, we don't want to have like 5 in the first, 7 in the second, 2 in the last, is because here we want to be able to trivially check if the number of columns we're trying to access is greater than the greater than or equal to, again, for the same reason as the previous one, the length of any row's number of columns. And so that's why I put this 0 here. That's to find us our axis. That's to basically ask us, okay, the 0th row, so this row, how many columns does it have? And we're going to treat that as the same number of columns as all the other columns. So if we start doing these kind of shenanigans, we'd be in trouble, because this check is going to prevent us from checking outside our grid only so long as all of our columns are the same length as this one, as the first one that's listed. Now, as long as we've determined now that we're safely in bounds, okay, these rows and columns correspond to a valid position in the grid, then instead of returning space at the bottom, we're going to return, is just like we do here, a world grid check against the row and column, but it's going to be the computed column and the computed row. So now we find that the player is at a certain tile position. And let's print these things out somewhere. Okay, let's text. Let me double check our arguments for the order. So we have there we want to print stuff. In fact, I'm going to borrow the whole line of text here. I'm going to paste that there. Except I'm going to put this at mouse y plus 25. So then below the player, we should see which row and column the player corresponds to. And so let's see, remember, so column is how many x, row is how many y. I'm going to line break these. Remember, white space, as always, doesn't affect code. It's just for readability for our own purposes. And so there we've got the column and the row. We're going to see that listed below y plus 25, so below the positions we still have to call this function from somewhere. So here, before we draw the player, let's say if what's under this coordinate, player x, player y, equals equals, I'm going to do a line break. Let's say grid type wall. So if we're standing on a wall, then we're going to fill the player with yellow. Otherwise, we know we're standing on an empty space. And let's make the player cyan. Okay? We're going to be yellow if we're standing on a wall. And otherwise, this else condition, notice these braces that I sneak in there. So these two braces match up. These two braces match up, just like parentheses. Anytime you open one, you got to close one. We're going to make it cyan if you're not standing on a wall. And we should see, oh, let's see, my mouse cursor seems to be covering up those numbers I want to see. Let's add more than 25 there to the debug output. Let's say plus 50, hopefully will put us underneath the mouse. There we go, okay? And you can see there, so it shows us, in addition to the player's coordinate, which tile it's computing. So as I go below 80, it clicks down to 1. And notice too, my ball changes from cyan to yellow as I step over the wall. And up here, it shows me I'm in position 0, 0 in the grid. And as I walk up, you can see it's increasing which column it's finding. And I cross there, I'm into a wall now, so it makes it yellow. Notice too, my font changes coloring based on the player character because of where we display this code, but yeah, you know, no biggie. Notice too that when I step outside the grid, I don't see any number represented below the mouse. See how I'm in 7, 0? Now it doesn't show anything at all. That's because these are our safety checks that are checking to make sure that our row and column are within our 7 entries, or 1, 2, I guess 8 entries by 5 entries vertical. And if we exceed either one, then it bails out of this function. It's returning a value before it even gets to this text call, which is why we don't see it, which is why it's also avoiding this array check into a position that would be illegitimate. Notice too that again when we step over a wall, which our walls are being colored as, so if there's a wall there, we're drawing green, and if there's a wall there, we're making the character yellow. See how when we step over a wall we turn yellow, when we step outside the map we turn yellow too, because we're returning wall value here, meaning that if we step outside the grid, we're going to treat it just like we'd run into a wall. Okay? And that is going to let us handle our player's collision detection so that if it steps into a space where it shouldn't be allowed, we can bump it back. And we've been showing these grid lines just kind of by default because borders are showing, but right at the start of the world draw grid, let's say no stroke. Looks like I'm a little bit indented more than I need to be. Let me unindent that. I unindented a whole block. I used shift and up and down arrows to select multiple lines. I then held command and used left and right brackets to indent and undent entire blocks. But no stroke here should take those black lines off of our rectangles, and that'll help our map grid blend together more nicely. And you see, okay, you can still pretty well tell it's a grid, and you can still see how it corresponds to the numbers in our grid, but it's not quite as blatant. You know, it doesn't show you literally like the lines like a checkerboard would. But so we're same situation. We're cyan when we're on red, which is ground, yellow when we're on the green, which is the wall, and if we try to step off the world, we turn yellow. And of course, same story, if we step off the top of the map, we turn, oh, because of the division we're doing, it's not quite handling it the way we expected. There we go. Okay, yeah, we're getting a truncation. So, little bug found. Here, if I step off the left side of the map, notice how it still shows me 0 for which tile it thinks I'm on until I step all the way into -1 tile. So really the safer check there isn't to even check the row after we divided it, because the division is losing some of our accuracy from the integer. Instead, we're going to check and see if our row is y, column is x. We're instead going to check and see if the player's x or y coordinate is left of the left position. And if so, to bail on that condition, and that's going to, yeah, that fixes it for us. So now if we step off the world map at all, it immediately tells us we're on the wall. And you see our text color changes on the mouse as our coordinate does too. So that's why for the bounds checking on the left side, I'm going to use the coordinate itself rather than the row division. Okay, so let's now handle the condition where when the player steps onto the wall, we want to bump them back to where they were. There's different ways you can handle this. We could try to anticipate it and block the player input based on that, or so on. One easy thing to do is to make it a part of our key handle states. So this material here, that's what is under the coordinate for this grid. First of all, let's remove that debug output line. I'm going to get rid of this text call because this doesn't really need to be there, right? I mean, we could comment it out if we just want it back for later. We could do a /star to //, and then we'll just ignore the code. I'm going to knock it out of mine though. We only need draw code and collision code, right? I'm going to take this code that handles the player's movement, and instead of making it about fill color, we're going to use that to decide when to bump the player back to a previous position. Okay, so I'm going to steal this if. Actually, first let's delete this else. We're going to set the player to always be colored bright white so we can see it against different backgrounds. And instead of filling here, we're going to bump the player back. But let's make this now part of the movement code and handle key states. Okay, so I cut this if condition with the comment I stuck in there. I'm going to go to handle key states, which is in keyboard. And so see here, so we're moving the position based on how the player moves. What I'm going to do is I'm going to say int px was equals player x, int py was equals player y. That way, I have a saved value for where the player was in the x and the y coordinate before these key movements got processed. And at the end of it, I'm going to paste, there's my function, what's under this coordinate, player x and player y. And if it's a wall, then I can undo the player's position by bumping the player back by saying, okay, player x equals px was, player y equals py was. See, so I saved the values of where the player used to be before we updated the position. Once the player's position has been updated, if the new position is on top of a wall, then I'm going to undo the movement we had just done by smashing back over the change we just made with what the values were. Does that make sense? And again, as always, so we nestled braces. This is end of void handle key states. Comments just help clarify where we're at. End of if checking whether player bumped wall. And when I press play, we have a white dot, as always. But now, if you try to move over green, your character will get stuck on it. If you try to leave the map, your character will get stuck on it. See, I try to walk on the green, and I can't. The center point of me won't allow it. Do you see that? And that's simply doing a check to see if the value coming back from it is of type 1 when it does the divisions. It's all happening exactly as we've seen before. It's taking the player's coordinate positions, like right where we see where the mouse is printed. It's dividing them by the width and height of each tile, 40 in this case. And if the player is stepping onto a tile where there's a wall, where we're drawing green, it's undoing the player's movement from that episode, or from that movement. As an additional extension of this, so right now we can't really slide on walls, we get stuck. There's different ways we can handle separately to figure out which of these is responsible for us to be going over a wall and then allowing the other one to happen freely by using this what's under that coordinate check. If we want to have a new type of tile, let's say we want to add a coin type of tile just for fun. Coin. Let's call it coin number 2. Okay? I'm going to put a coin up here, then coin down here, coin down here, coin over here, and a couple coins down the side. See where these 2s are? Now, before we've done anything at all, if I just press play, you'll notice that they currently don't look like anything. And I can walk right over them. Because we've explicitly handled the wall condition and code, but we haven't really addressed coin, it's right now just being caught as an else condition for what else to draw. So we have to change again to what we're going to draw for the coin. Now, one thing we could do here is we could make another else if like this. We could break this out into, and we can have a number 2 there for a coin. We could make this a switch case in terms of having switching on that, whether it's case 0, case 1, or whatnot. And in fact, let's go that way. Okay. Now you might already notice down here we're starting to have these funny 0, 1, and 2. Doesn't really matter, of course, where we assign these colors just yet. Now, we already have the problem of these 0, 1, 2 don't mean anything. Remember, that's why we have these labels up here, because we can use these labels in place of those numbers down here in the code, and they will be easier for us to look at. So when we skim through this, we can remember, okay, wall, what color is wall? Without having to think about what number wall has been assigned to. It's just a handy thing to use constants for in programming code. Okay, and now right now we've got, so space will be green, which is backwards from how we did it, so we don't confuse ourselves. Let's keep space red. For wall, we have, let's make walls red. Now what color should we make coin? Let's initially just make coin yellow. It seems applicable to me. And now when I press play, there we go. So we've got, oh, I seem to have reversed space and walls. Walls were red. I undid that a second ago. My apologies. Space red, wall black, or wall, actually no, let's make space black. How's that sound? I think that seems much more natural mapping. And now to avoid confusing it with the empty space outside the map, you can see here where it's redrawing pure black. Let's make the background area of the world a gray. Oops, okay. Background shade, I'm going to make this shade 200, which is going to give the background a grayish tone. There we go. Maybe even a lighter tone, 100 will work. Just so we can see, okay, over here is gray, that's our background call, wiping the whole area. Black is movable space, green is a wall, and yellow is a coin, which you can see we can currently still move over because we haven't handled collision code for yet, we've only handled draw code. It does correspond to where we've placed 2's in the grid, so that much is positive. And we've got something we can understand as to what's going on, but we can walk right over it. We get stopped by the green, we walk right over the yellow. What should happen when we get a coin is, of course, we should collect the coin. And what we can do for that is we can check and see what's under the coordinate, handle key states. So we could do another check and see if it's, let's walk back through the switch case, by the way. I don't know if maybe that's newer to you. This is basically just an if-else chain for when they have a single integer to compare. So we have a single value once. So it could be a one random number. It could be, in this case, the tile value, an integer at a coordinate. Could be handling different logic state values or something. But then we can narrow it down to, okay, for this case, do these things. For this case, do these things. And unlike most other constructions like if-else chains or while loops or for loops, rather than using braces, cases are eliminated by using break, which is what tells it to bail out of the switch statement without going further. Alternatively, you could use a return, which of course would bail out of the entire function and stop drawing the rest of the grid. We just want to bail out of the switch condition, so it'll only run this code, and then it won't run any code below it in the switch case. So it's sort of an antiquated structure. They still come up from time to time in this sort of environment, this sort of setting, in C or C++ or ActionScript 3 or other pretty common languages. Okay, so here we could check the player's coordinate again to see if it's a coin. We're already checking it once. So let's cache that once and say int tile under player equals what is under this coordinate player x player y. And now we can check and see if tile under player is grid wall, then we're going to return the player to where the player was. And again, we could do an else if tile under player is coin. We can turn this into a switch case. I guess I'll actually keep this one an else if just to show you kind of a comparison of how the two look. How this one's a little bit more bloated, a little more hard to predict what else might happen in terms of, you could do inequalities here, right? You could do algebraic expressions on either side and so on. As opposed to a switch case is strictly for checking, is it 0, is it 1, is it 2, which is really exactly the kind of thing we're trying to do. I just want to show you kind of a contrasting example. So if the value under the player is a coin, then what do we want to do? Well, we want to make the coin disappear. How would we make the coin disappear? Well, so we already have a way here to find the tile value under the player, right? What's under this coordinate. Let's make a new function. I'm going to copy this entire block of code, which is doing a sort of a safety value check on coins. And from that block, well, I'm trying to figure out if we want to pull away some functionality here to make it a little more generic. Okay. Because we're otherwise going to duplicate a lot of code, which I try to not get too caught up in doing or discouraging, but we're going to say safe tile, safe pixel to tile X. Okay. I'm going to pull out some of the functionality we had here and make it into a separate function for X and Y. So column is going to take some value of X in. It's going to find the column for it. It's going to return. Okay, I'm going to backtrack on that. We're just going to duplicate the code for now. This is going to get slightly complicated versus what I feel like showing for now. So, want to keep it at a concept level. So int, what is under this coordinate? I'm just going to copy that entire function. Int, what is under this coordinate, all the way down to the closing brace. I'm going to paste it. So I now have that same function here twice. This is now a separate one. I'm going to make this one to change tile under this coordinate. I'm just going to call it change tile. And I'm going to say some x, some y, those are pixel values, of course, int change to. Okay? I'm going to make this void because I no longer need to get back what kind of tile was underneath me. We're going to take in, and we could journalize this somehow more nicely. For now, it's going to be sufficient because we just want to kind of move to the concept, like I say. Change tile, we're going to give it a pixel coordinate. Okay, not a tile coordinate, a pixel coordinate, so like where the player is, and what we want to change the tile to. So we can do these same checks for safety, although instead of returning a value, we're just going to return to just quit the function so that we don't accidentally try to make a change to where the grid isn't. Okay, so I've gotten rid of the values because we're no longer returning an integer. We're just going to, as a void, it's just going to call the function, trust it, do its thing, and then come back to us in the code. We're going to return if it's anywhere out of bounds, but if it's in bounds, instead of returning the value at that tile coordinate, we're going to change the value there to change to. Do you see what I did there? So instead of returning this value, we're going to assign into that coordinate space in the grid live, we're going to update the value here to what we change it to. Okay, and so now we have this new function called change tile. We're going to take a pixel and what we're going to change it to. So here in keyboard, if the tile under the player is a grid type coin, we can change the tile under player X, player Y to grid type space. See, so when I step on the coin, if the tile detected under me as a coin, then we're going to update the one under my player coordinate to space, which will remove the tile from the grid. See, so I can still bump up against walls. When I bump into a yellow one, boink. It's clearing it because it's updating the value in the two-dimensional array to our space value, which is just an integer for 0, just a predefined constant. And then when it finds it, it's eliminating it. We can make this slightly nicer if we want to. So here, like right now, we're just drawing the coin as a yellow square. We could, for example, draw the coin's square, still with a black background, just like we do the other stuff. But then we could draw an ellipse inside of it that is horizontal position here will be the same as the left side of the tile plus half the width. The vertical position will be the same as the top of the tile plus half of a tile height. And then our ellipse size would be the width and the height. Just because remember the ellipse by default drawing from the center. So we have the top left corner plus half of the width will put us in the center of the tile. Top edge plus half the height will put us in the center. And then the width and the height. So we're going to draw a yellow circle in the middle representing a coin. Followed by, followed by the fill color black, which is still going to draw the rectangle underneath it. And that didn't quite do what I hoped. Oh, that's right. It's because it's drawing the rectangle on top of it. That explains what's going on. So yes, if I wanted to display that, I can move this. I'm going to move the rectangle call up here into draw space. So draw space will draw just a black rectangle. Draw wall will draw just a green rectangle. draw a coin, I'm going to flip the order here. So it's going to first draw a black rectangle, and then it's going to draw a yellow circle. When I press play, there we go. We now have something that looks a little more like coins. I mean, they're not perfect, but you get the idea. We could, of course, figure out from this how many coins we have left in the map by iterating through it. We could, when the program starts, loop through and figure out how many coins we have. Let's say we can, let's do that. It's a good little quick exercise. Int coins in world equals 0 by default. Okay. Int count coins. Let's just say void update coin count. Okay, we're going to start off at 0. And then, so just like down here, we can loop through each tile in our grid based on what's in it. I'm going to copy those lines of code. Again, careful not to get lost in these all these layered braces. End of void that. End of for row. End of for call. End of if world grid at coord. So if the world grid at a particular coordinate equals grid type coin, so it's going to look at every single row, every single column within that row, and check and see if the value at that row and column is the type for the coin. Then it's going to add to it coins in world plus plus, so that by the time this function executes, it's looked at every single grid spot to determine how many number 2s, how many grid type coins it found inside the grid. And let's display that number on the screen somewhere. Let's say down here in the bottom right, text. Mouse X, mouse Y thing's been pretty handy, but we probably don't need to keep doing that. I'm going to get rid of this player X, player Y coordinates. Knock that out. Let's say width minus 100, height minus 30, and I keep forgetting if text comes first. Okay, plus coins in world. Actually, we probably don't even need the quotes there. Whenever you see me do this thing where I put a quotes and then a plus, I'm just forcing it to be a string, because this is a way to trivially concatenate into a string as opposed to this is an integer, but I bet text is going to accept that too, probably. Yep. Okay, so right now when I start, it says 0 because we never actually have called coins in world. But remember, a great place to call update coin count is here inside setup, because we know that setup gets called once when the program starts. If we had a reset button, we'd want to call it in there too. Okay, it says 7. Let's count. We have 1, 2, 3, 4, 5, 6. We have 7 coins. It says 7 down there. Let's try adding another coin just for testing sake. Stick a 2 up here. Press play. We have 8 showing up now for this number down here. And remember too, we can trivially make this world any larger we want. We can give another row. I can duplicate the columns. Or I can give another column, then duplicate the rows, cut some holes in it, make some changes to it. Whatever I do down here, as long as our commas and things still build a rectangular grid, because of how we've written those for loops, it's still going to work out. So you can see we now have 9. 3, 4, 5, 6, 7, 8, 9. Okay? Pretty easy map so far. And of course, so just like we were detecting when we step on a coin to replace it, we could check and see if we step on a door and we have a key item. Replace the door, remove your key from your inventory, or otherwise. You can make this a navigable space in other ways. But so, let's see, where were we? All right, we have a coin count. But right now, when I collect a coin, that number doesn't change because we're not changing it all. 9. It should say 8 now, right? 7, 6. Now, there's different ways we can handle this. I could constantly call update coin count, but that's not really necessary because the coins don't change that often. I could call this right after the player has done this change tile count, and this would work, right? This would only, right when I collect the coin, it would loop through everything and then check how many coins there are on the map right now. But a smarter way to do it, not really that tricky of a way, is we have this coins in the world number already. I can just say coins in the world minus minus, because I know that each time I got exactly 1 coin when this happened. So now that number will count down. 9 turns to 8. Turns to 7, turns to 6. I might want to make another variable called int instead of calling it coins in world, total coins in world. Right when I've done my first calculation for updating coin count, I can set that equal to coins in world. So all I've done, I've made another variable, total coins in world. Right when we first compute how many coins there are, I set it equal to the coins we just counted. And now, instead of printing out just coins in world, I can put a slash, and I can show like this many out of how many total, right? So it'll say like 9 over 9, and 8 over 9, and so on. It's kind of a nice way to be able to display it. See, it says 9 over 9, 8 over 9, 7 over 9, 6 over 9. This is a handy way to do it for all kinds of values in a game or game-like environment where you have health values that change, where you have ammunition that changes, various types of power up with timers and so on, numbers of enemies in a level, where you don't want to totally lose track of how your world started in terms of the quantity that were there. Speaking of which, you'll notice that because we're changing the world each time we play this, or each time we collect these coins, right now we couldn't really reset this map because we have destroyed the only information our program had about where those coins were. Two options for doing that. One is we could have a second array that we copy, that we could use this as like our map data, and when the level starts or resets, we could copy the map data into our live array and then modify that one safely. Or more likely what often happens is we'd have this information in an external file where we would use load strings to process this file using the code I showed in one of the previous videos from this series. Load strings could be used to then parse this into filling a two-dimensional array so that we could then use that as our map data, and we just reload the file externally whenever we want to replace the map as opposed to from something in hand-typed in memory. Those can also be handy because once you have an external file like in a load strings array, you can visualize it in Microsoft Excel. You can make a little editor to control it and save out that file, even in processing and so on. Your own map editor, but you get the idea. And right now, when I collect the last of the coins, nothing special happens. But what if, let's make a little condition here, if coins in world is equal to 0, else, and again, as always, open and close braces need to match up. Open brace, close brace, open brace, close brace. Then I'm going to print a different message. It's going to say, you win. And that's simply the same as checking if coins in the world is equal 0, meaning we've collected the last of the coins. Okay? 9 is 9 to 8, 7, 6, 5. And again, can't go through walls because we're handling that collision. 3, 2, 1, and 0. You win. There it is. Now, of course, there's a whole bunch of other ways we could play with this program. We could display an image of an avatar, for example. And actually, that's going to be a useful thing to show. I bet lots of folks are wondering how to put their character in there. So let's show you how to do that. We've saved our file already. If you haven't, you totally should. I went to just File, Save. I named it Sketch Grid Collide. You want to pay attention to where files get saved when you save your sketches. And you can probably use just Save As to double check. But on most machines, it's like Documents or My Documents, Processing Folder, and then a directory with some sketches in it. So I'm going to go to where that directory is, Documents, Documents and Processing on my Mac, and again on Windows it'd be on My Documents Processing probably. I'm going to go to the one I've just saved, Sketch Grid Collide. And there's our, you can see just like we expect, our Sketch Grid Collide's our main file, always has to match the folder name. Keyboard and World PDA files, not even separate classes, just files to keep us organized. And now let's have a data folder. New folder data. That's where I can put images or sounds to load. This is going to be a little quick review of what we already had in the image sequence. Now I've already made a little image in advance that I'm going to copy into there. Just character.png. It's just a little 32 by 32 pixel image. You can make that any way you want in Photoshop or Blender or whatnot. I'm going to open it up in Photoshop real quick. Okay. And now notice too that this has transparency in it, that this has blanks around the edges. The way that I did that, just to kind of show you from fresh, I made a new image that was 32 by 32 pixels. Okay. And notice that by default it has a white background. I don't want that because I want to be able to see the background around the character, right? Not just white box square with a smiley face in it. So I created a new layer, which I realize is off the camera. Let me move that in. There we go. So I created a new layer. I then deleted the background, and you'll see the checkerboard. That's how you know in Photoshop that you're looking at a transparent region. I drew a circle, holding down Shift to keep it symmetrical, or to keep it certain fixed dimensions. Okay. And you can see kind of the gist of what I would have done here. Got my yellow out. Pop, 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 pop. This one would actually be a little more freeform looking because I'm just going to do it with some freehand instead of using. Oop. A little too much, little Control Z there to cancel it. Sample strokes, making a little smiley face type deal. Close enough. A little blackout, small brush. Say 4. There we go. That'll work. And in fact, I'm going to replace my other one with that picture, so you'll see it with that. Okay? Don't save. Photoshop. But the important thing is we have a character.png file there in our data folder. And so now at the top of our file, we need to indicate pimage, our hero. In setup, we have to load that file, so equals load image. And here's where we put the file name. I like to copy and paste these. I know I've mentioned before, but if you don't see the extension, that PNG or that .jpg or .gif or whatever, then your file extensions are currently hidden on known file types. And whether you're on Mac, Windows, or even Linux, that's going to throw you off. As a programmer, you need to be able to see file extensions to tell what type of image format you're working with, to tell whether your HTML file, if you're working on web code, is ending in .php, HTML, HTML, etc. That's always, so in Windows, that's folder options, access to your control panel, and Mac, it's through your preferences. But Google, how to show file extensions on known file types, or how to file extensions hidden on known file types. Google that kind of thing for your operating system. If it's not showing you that, you'll want to make sure you can see your extensions. Okay, so here's our hero. We loaded the image for it. And now, we're just going to display right here. This is all we were doing to draw the player, right? We had this white circle right there. We're going to comment out the white circle. Actually, we're going to keep the white circle there for a second. I'm going to show you why. Image, our hero, and then I think we need to give it an X and a Y, or vice versa. We'll find out pretty quickly. That worked. Okay. And now notice that, so there's our hero's circle. Notice that the white dot is up and to the left of it, because remember that an ellipse draws from the center of the coordinate. Player X and Y are the center of that ellipse, whereas our hero image call is specifying the top left corner. So if we want this to display centered, then the way we need to do that is we can subtract half of our image's width and half of our image's height from the position of it. I'm going to move the ellipse call to after our image so we can show that this worked. And see how the white's in the middle of the nose? By subtracting half the width and half the height, we've centered the image. So the coordinate we're drawing from is already pre-accounting for the dimensions of our picture, like so. We can get rid of the ellipse. I'm going to leave the fill there because that's actually coloring our text that shows up in the bottom part of the screen. There it is. Yellow space, eating coins. And of course, we could try to animate it. We could do other fancier things. We could build a bigger map that scrolls based on where the character is on the screen by having an offset on everything. But we're not going to cover that today because we're kind of running low on time. But we can collect coins now. It says you win. It's kind of a straightforward little game, if you want to call it that. But it's a technique that's really handy for using optimized collision detection. If you could have a lot of characters, realize that for each one of these to check where they are in the world, it's just a single X and Y division by the tile dimensions to figure out where they are in that environment. Remember that we can pretty easily change if we want to make that world a little bit bigger. 46. We now got a bigger world to navigate in. And if you're wondering, okay, well, my character can go half over the walls, how do we fix that? Slightly more advanced way to handle this collision detection is to, instead of thinking of it just as a center point in the middle of the character, we can start to look at, okay, the bottom of the character is the character's center point plus half the character's height. The right side is the character's center point plus half the character's width, and so on. And we can check and see if the player's right side's up against something to bump them back just enough to make the right side line up. And that's really how you start to handle better collision detection for an environment where your character feels more solid instead of like a single point in space. But thank you for tuning in. Hopefully it's been helpful. I know this is really applicable to games types of folks, but maybe not as useful to other folks who are interested in other uses of digital media, but games being digital media, I think it's got a lot of application for folks out there, no matter what you're working on. Thanks for tuning in. I'll have, as always, more videos coming up soon for more material for these courses. Thanks again. Chris DeLeon for LMC 6310, signing out for now. Bye-bye.